All right then. So good afternoon, everyone. My name is Dapo Sosanya. I'm a control systems engineer, and I'm privileged to present this information session today. And I'll be talking about a project that we've been working on, the Decentralized Wireless Mesh Connectivity Suite with embedded AI. And that's a low power mesh networking with on-node intelligence, initially targeted at the oil field environment and other vast remote sites where communication infrastructure is either absent, unreliable, or unaffordable. So we'll be looking at this topic in under six agendas. We'll look at the problem. We'll look at, define what the DWMCS-AI is. We'll look at the mesh stack and the edge native AI that is peculiar to it. And then we'll look at the AI, the one engine, three workloads, the self-healing, and then lessons for builders. So the problem. So this is a typical environment where this protocol is designed for. Very vast environment where you have assets scattered. This is one of the extreme cases. This is the Gulf of Guinea, where you have oil wells scattered across what you can see here. So that's how harsh the environment will get. And in spite of this, operation still needs to continue. The remote assets needs monitoring, and data needs to be delivered to the production platform. So that's a typical use case. So the problem, as we saw the environment, the challenges we have today is not a challenge. It's not a challenge of sensors. It is a challenge of connectivity. In such environments, there is no network coverage. Even if there is cellular, it's weak. We can't run fiber, submarine fiber. It will be too expensive, cost prohibitive. Satellite is also too costly. And then we quickly run into regulatory challenges that says that certain data cannot leave. Sovereign challenges. And then by the time we get to know that a particular well is not functioning, it is too late, or most often it becomes a reactive action. So there is a need for a real-time and predictive delivery of asset conditions so that we can operate with efficiency and with increased value. So these sites do not need a cloud-first product. They need a site-first one. A solution that keeps the decision locally, even when the link to the outside world is down. The single requirement shapes the entire architecture. So this is built for the oil field. We have wellheads and flow stations. We have pipelines crisscrossing complex environments, the water, the swamp, the forest, the open field, places where humans live. And then we have legacy instruments that are still functional that we need to acquire data from remotely. So the scale of the gap, for example, the Niger Delta alone has 275 flow stations and over 7,000 kilometers of pipeline, and most of it without continuous wireless monitoring today. The prototype for this solution has been demoed on a farm, which mimics the large geographic area of the oil and gas environment, even though it's not as harsh. It has been demoed on temperature, humidity, and air quality in pen houses, and it has also delivered presence detection within the perimeters of that farm. So it's been proven, the concept has been proven, right? So what exactly is DWMCS? DWMCS-AI is a site-first mesh protocol. It works without the cloud. It is a network of small wireless nodes that each sense, process, and communicate. The mesh can self-form, they can relay data across multiple ops, and can generate local alerts. So the one-line version, DWMCS brings reliable monitoring to farms, to mines area, to remote industrial sites where cellular network is weak, where fiber is too costly and satellite unaffordable. It relies on sub-gigahertz mesh with on-node intelligence so that existing instruments can join the network and fire alerts even when the internet or outside connectivity is down. The protocol is built around 4 capabilities. We have the sub-gigahertz mesh, we have the edge intelligence, then the protocol bridging, and then the staged AI roadmap. So this segment will explain the mesh stack and the edge native AI, how it's implemented. So we have essentially 5 applications when you want to deliver data. You move from, depending on the direction, the sub-gigahertz LoRa. So the protocol is standard agnostic. It can work with different standards. So using LoRa as an example, you have the radio, which is long range, but low power. And then the MAC/link layer, who transmits, that determines who transmits and when, right? And then we have mesh networking. And that is where the innovation is. The self-forming area, and that can arbitrate multi-op routing. And then we have the transport layer where you have the fragmentation and reliable delivery, and then the application where you have the sensing alerts, the edge logic, and the edge logic. So the inference runtime runs on the mesh routing layer. So a model's output can change how the network behaves. What we are trying to optimize for, because of the harsh environment, power also is an issue. So the routing algorithm selects the best path that gives the cheapest cost for the data delivery. The edge native means a specific layer. So the conventional method we have presently, right? It's network blind. It doesn't look at the direction, how the data gets delivered, right? It runs as an application layer, right? It sees the sensor data. It doesn't see the network. And then it outputs alerts and nothing more. But edge native sits at the inference sits at the routing layer. Because it's a mesh, one node can have X number of options to transmit. The inference engine will determine the cheapest option amongst those options. It considers power and it considers the link quality. So edge native in this instance means that it can see both the asset and the network, right? So output can change network behavior, unlike before where the network is opaque, right, to the node. So in the work, we have, we use some existing technology, the Zephyr RTOS, the open thread, and the standard LoRa physical layer, right? So what we are doing is we are running inference into routing. We're using AI to intelligently route and to also minimize power consumption. We are running predictive routes. We are doing semantic protocol bridge, right? And that enables legacy instruments to function in such a network, right? And then there's the federated learning over a 10 kbps link. So the AI, one engine, three workloads. So three engines, three workloads. We have the anomaly detection that watches the physical assets, the predictive routing that watches the network's link, and then the federated learning that improves the models on site over time. So it's a purpose-built runtime that loads a model into a few hundred KB of RAM and runs a forward pass on a microcontroller from right inside the mesh stack. It is model agnostic. It doesn't care whether the model watches ammonia or radio link. So, this is a further description of the three features. So the anomaly detection looks at what the sensor is watching, whether temperature, whether pressure, whether humidity, whether ammonia, and then it decides whether the reading is within or outside the operating envelope, the desired operating envelope, right? And if it is outside, that is when it's going to raise an alert, right? The physical world the node is instrumented for, it answers a question about the asset, not the network. That is what the anomaly detection does. The predictive routing uses factors like RSSI, signal to noise ratio, packet loss over a window. Those are the things it uses, and then power to determine the cheapest network route to send a data over. And then the federated learning. The job of the federated learning is to improve the models over weeks. Nodes compute updates locally. Updates are compressed and partly aggregated at relays, and then the model sharpens to each site. So the constraints that makes this problem very interesting, we're doing tiny compute. We have tiny compute, hundreds of KB of RAM on the node. Model size and quantization aren't optimizations, so we have to design them. We have a 10 kbps link. So we have a 10 kbps link, sub-gigahertz LoRa, which is very narrow, right? Then energy is also a constraint. And then we have the relay load. Those are the constraints that we are designing and building around. Now, so we have in our lab test, of course, it's a lab test. We've achieved F1 score of 0.92. This is not a field validation data, right? It's going to be significantly different in the field, given the nature of the F1 scores. So like I mentioned earlier, the self-healing has been demonstrated already. So essentially what that does is a sensor has the point, a point of view, right? The sensor can see two or three other sensors at the same time, right? And it can route data through any of the three. So if it prefers, let's say, line A, And if line A dies, right, it will automatically route to line B. And if line B is not available, it automatically routes to line C. So there is the add bit that monitors the link and then check whether a link is lost, select an alternative route, and then reroute the data and then re-forward. So that's just a demonstration of the testing that we did for the self-healing. So we had a tank A, which is 15 feet high, that is receiving data from penthouse 1 and penthouse 2. Then we have a feed mill that is at the remote end of the farm, right? That feed mill normally can see penthouse 1 and penthouse 2, but it cannot get to tank A directly. So we took out the connection for between feed mill and the penthouse 1, and then the data automatically gets routed through the penthouse 2. So that provides what we call a path redundancy. So I will just jump into the lessons for builders. I mean, based on what you are building, it's important to design site first. You know, the theme of the context is local AI. So you design site first, you assume the cloud is unreachable and make the node useful anyway. If your model only works when connected, it won't survive the field. And then budget your energy honestly. So power isn't dominated by transmit power. It is the time the data is using in the air and the relay load that determines the power that will be used for that particular delivery. A cheap long up can cost more than several short ones. So a lab metric is a hypothesis, not a result. I mean, you need to have that in mind when you're building. You can have an excellent lab metric. It's just a basis for you to proceed to the field test, because there are so many other factors that comes to play when you have to do your field test. So you need to pay attention. So if you take one idea from this talk into the challenge, your F1 on a clean data is the ceiling, not the number. You need to plan your field validation loop from day one. You know, you need to make sure it captures real events, it measures the drop, it tunes to the real cost of a miss versus a false alarm. And then the problem should actually pull the capability. You know, sometimes we sit and we design a series of problems and hypotheses and everything, and we just create our design to suit that. We need to ensure that the problem is real, right? So, for example, the strongest feature when we're doing our test on the farm, the goal that we're testing for was to detect ammonia and temperature within the pen house, right? We never planned to test for a predator, but along the line, the owner of the farm mentioned that they have been noticing a predator coming to disturb the birds. And then we say, okay, we can interface a presence sensor to the system. And that was when the feed mill part came into play. We interfaced the presence sensor, and then immediately that presence sensor, sees the predictor. It's actually detected the predictor about a few times, right? And then it routes the data to the central location. So the takeaway, proving in the field, and then there is the work to prove our work in the field is still ongoing. The bench lab, we have some results from the bench and the lab. And we're working. I mean, as soon as we get all the necessary approvals, we'll move to the field to validate, right, all the hypotheses we've gotten from the bench, right, in real field environments. So thank you. And questions, if there's any.
Hi, Dapo. Thank you.
Yeah.
Thank you so much.
Okay, in my head, I thought there was nobody on the call, so that's why I rushed through the slides.
So I mean, are there parts that you'd like to emphasize?
Well,
Are
maybe
there
if there are questions, I'll be happy to
to
take them.
respond?
Yeah.
Okay. Um, so welcome once again to everyone who joined as Dapo was giving his presentation. So Dapo, please, in just for the people who missed the first part your of your presentation, please can you just go over the yeah, so DWMCS AI model. Can you just go over it? What it means,
Okay.
why it is important for builders to take note of it, especially when on this side of the world and for like real life use cases.
Okay, I'm happy to do that for me.
All
So,
right.
session, and it was targeted at people that are building solutions towards the challenge, the African Deep Tech Challenge. So I thought to use a similar project we're working on, right, as the basis of that information session. And this is the solution. It's a protocol suite, right? We call it the DWMCS-AI, Decentralized Wireless Mesh Connectivity Suite with Embedded AI. And it's based on real and observed field systems, right? I showed this image earlier. The protocol was designed or is envisioned to function in this environment. This is an oil field. You have valuable assets scattered across this oil field. To get from one point to the other, you either go via boat or via helicopter, right? Let me just play this video. So that is how harsh that environment is. And you can see there's no mobile mast in sight, right? And it's almost impractical to carry a data. I mean, we want to carry a data of, let's say, 5 KB, 5 kilobytes. What am I even talking about? 10 bytes, just a sensor reading from a transmitter. Then you first have to connect to a satellite. So the only sure communication means in this environment is satellite, and it's cost prohibitive, So that led to the need for a protocol that will be able to acquire the data, perform intelligence in situ, right? And then report the data as at when needed. So that is the vision for the WMCS AI. And I mean, in the Niger Delta, Nigeria, we have almost 275 plus flow stations, 7,000 plus kilometer of pipeline, over 10,000 individual wellheads scattered across. And all of these are very valuable assets that cost millions of dollars. Yet we have very limited insight into how they operate day to day. So while developing the solution, we've been able to prove it on a farm environment, the technology at least, right? We've proved the self-healing mesh network. We've proved the data delivery, and we've done some work on the bench, on the AI engine. We've gotten a very fantastic F1 score. And like I mentioned, the F1 score, we are seeing it as a ceiling. We know, given the nature of F1 score, by the time we get into the field and we have real data, it will be much lower than what we have. So that essentially is what DWMCS is. It's a means by which we run data delivery and asset monitoring in very difficult environments. And it is built around these four capabilities: sub-gigahertz mesh, protocol bridging, edge intelligence, and staged AI roadmap. So that's the networking layer. And the strength of the solution is that we can run AI at the network level. We use artificial intelligence to determine how we route data. We are not using it at the application, which is the conventional method. The conventional method does not see the network layer, right? But because of the harsh environment, power is critical. Real time is critical. So we have to deploy intelligence at that level so that we can get the best results possible. Yeah, I think that's essentially the summary for what DWMCS-AI is. Thank you.
All right, thank you. Thank you so much, Dapo. Thank you. Okay, so anyone with any questions for Dapo, you can either use the chat or use the Q&A. I think there is one in the Q&A. So is the protocol to be deployed on IoT devices in production? This is from Emmanuel Aruso.
So we have presently we don't have we have deployed this on some Texas Instruments chip, right? Sorry, can you read the question again? Let me be sure that I get the context.
Awesome work. So is the protocol to be deployed on IoT devices in production?
As in, is he asking if the IoT devices are in production as we speak? As in, have they been produced?
He's
The
asking
context of the
if
question is not clear to me.
So I'm asking if protocol that you just shared, if it yeah be deployed on IoT devices.
Okay, well, yeah. So the protocol can be deployed on different IoT devices, but again, depending on the environment of deployment, right? It has to be IoT devices that has been optimized for low power consumption.
Okay. Okay.
So that's essentially the hardware requirements, to use the protocol.
All right. So Emmanuel, please, can you confirm if you're good with the response or you still need more context? So basically, at the end of the day, the protocol you shared, do you need to design the specific devices that it will? Yes, asking more about the protocol. Is there like resource share for him to learn about it?
Okay, so as of today, the protocol is still work in progress. On the bench, we have everything done. It's presently, so the firmware and all the algorithms are presently deployed on the Texas Instrument microchip, right? We have about 18 nodes that is continuously running. So we're not in commercial production yet.
Okay. So that device was designed by you and your team, I guess.
Yes.
Okay. Okay.
So
All
this is
right.
our protocol. This is our we intend to develop it into a product and then get it standardized for use in the industry.
Okay. All right. So, somebody says, noted, can a Raspberry Pi or an Arduino kit run it?
Yeah, I believe a Raspberry Pi and Arduino kits. I mean, yes, can run it definitely. I mean, Raspberry Pi will definitely run it. I mean, because it has much more compute than what we are using presently. You know, Arduino kits also should run it. Yeah.
Okay. All right. All right, that works fine. Any more questions for Dapo? So Dapo, how can people reach you if if they need to get across to you? How can they reach you?
Okay, so I'm on LinkedIn, Dapo Sosanya, yeah,
Mm.
Dapo Sosanya CAP on LinkedIn.
Okay. All right. Okay. So if you can share that in the chat, just so people um who want to reach you can at least get across to you and learn more about this protocol that you shared. Um, okay, so another question is you mentioned that in the self-healing, AI decides the route. Can you expand on the AI algorithm you mean?
Okay, so of course, for every it's I wouldn't, I mean, with due respect, I wouldn't say complex mathematics, but again, mathematics is involved. How do you know that the quality of a link, for example, the things we measure the RSSI, we measure the SNR, right? So we continually, the system, the algorithm gets the value of the RSSI and the SNR as an input and then runs the model on it and then makes a prediction. So for the predictive value, right, it looks at the trend and then sees where the network would be, a particular link would be at time t, then decides whether that network will carry the data or a neighboring network. So the decision, a network, a link will have the shortest up, and then the algorithm might decide not to use it. So I don't know if that answer your question.
Okay. A follow-up question from Destiny Babalola says, so it uses time series forecasting.
One second.
All right.
Yeah, so I dropped yeah, so the follow-up question.
Yeah. So it's asking if it uses time series forecasting.
Well, so the specific technology, how will I say that now? Uh, okay, I don't know how to answer that, but what I will say is that there are the specific algorithms, right? It takes the real-time state of the link, right? And then those three data, what we're trying to where the compute that we have is very low, right? I mean, we're talking about a very small microcontroller with small RAM, right? So tiny ML, right? So it only takes about, I think, about 6 inputs into the algorithm, and then just runs that through, six parameters into that algorithm and use that for the prediction.
All right. Okay, so Destiny Rata, can you confirm that you're okay, or do you still have further questions? In any ways, this recording would be on YouTube after the webinar is over. And so anyone who's really interested in the protocol can go back and watch. And then Dapo also has shared his contact. So you can also reach out to him on LinkedIn or via WhatsApp, via the contact that is shared. Emmanuel, please use the Q&As just so we we can be respectful of time. We're almost at time. So if you have any more questions, you can use the Q&A. Um, okay. So, Dakwa, any last words before we wrap up? I see Emeka is on the call now before we call it a day.
Well, I mean, from my side, I'll just say that in preparing for the submission for the African Deep Tech events, it's important that the problem is original, right? It's important that the work also is original. I mean, it's important that the work is the problem is real, and the work is original. It rubs off on all of us if we begin to churn out quality work within the African ecosystem.
Yeah, very true. Thank you. Thank you very much, Dapo. Thank you. Um, okay. I don't know if Emeka is able to speak, but Emeka, are you able to speak and share something before we call it a day?
Yes. Hello, everyone, and thank you once again, Dapo, for such a great session. This is just to say hello to everybody watching, and we're looking forward to seeing your submissions. If you have any questions, do not hesitate to use the Discord community, and we'll be there to answer your questions either about this session or about the challenge as a whole. But yeah, thanks Dapo and Fumi for hosting this session. Thanks to those who attended as well.
All right. Thank you, everybody. And with that, we'll bring the webinar to a close. We have one coming up next week too, so please keep you can follow us on all our social media and also join the Discord channel to keep tabs on what's happening. All of the webinars that we have created is really to help you build to people who are looking to make submission to the Africa Deep Tech Challenge. We want to give you as much as we can, all the resources that you need to build something that is remarkable. And so these info sessions have been curated for that purpose. So please do well to join, to follow on social media, and to join the Discord channel. And with that, the Discord channel link, You will get that it's on our social media pages. To join the Discord channel, so we are at Africa Deep Tech on every social media. That's LinkedIn, Instagram, and you find the Discord channel there. The Deep Tech on every social media. So I feel like I should just share the link just so that, but I don't have it handy. Okay, yeah, absolutely. Thank you, Emeka. Thank you for coming to the rescue. Okay, so Emeka shared the Discord channel link in the chat. Please do well to join. That way you'd have your finger on the pulse of everything that's happening. We have GPUs, credits that are being distributed as we speak. So if your project needs some GPU to train the model, please do well to apply for the credit. And you get all of this information when you join the Discord channel. So please do ensure to join the channel. And that brings us to the close of today's webinar. Thank you so much, everyone. Thank you, Dapo, for making time for the session. Thank you to everyone who was able to join. Thank you for the engaging questions. We look forward to seeing you in the next one. Bye, everybody.